numbers. I think we talked about this a little bit yesterday already. And we've established about 10K resources managed per management server node. Pretty much scales out horizontally. Today, you do have to disable one particular component in our stats collector in order for it to scale out horizontally. And we have real production deployments of tens of thousands of resources managed. And in our internal software simulator, using that, what we were demoing today, we have been able to drive up to about 30K physical resources with about 30K VMs, so about 1 VM per resource with 4 management server nodes. And we believe we can at least double that scale with some changes. So this is how we kind of work on our scalability problem. One source of load of the system is got to be the number of requests that comes in. And on the management server, we have 2 sets of worker thread pools. One is provided by Tomcat. Pretty much anyone who does an app server knows that. And then we actually have our own job threads waiting on the job queue ourselves. And the way that we divide it is that if the incoming requests are mostly DB operations, and oftentimes when you're serving up a UI, that's the case, then these things are just executed by the executor threads, and the requests are returned back to the client. And we do that because most of the requests are already load balanced by the load balancer, right? But if the incoming request needs resources, meaning any of the physical resources, and this usually means these things have long running durations, and they would usually require a lot more resources, DB, things like that. So what we do is we check it against ACL, make sure the guy can actually execute that request, and then we queue it. We queue it into this job management layer, which today is backed by a database queue, and it gets picked up by job threads. So in multiple management server cases, then those job threads are basically spread across the management layer. Whoever has 3 threads will pick them up. The number of job threads are scaled to the number of DB connections available to the management server. So this is a bit of an interesting case, because you have to be able to see, look, I only got 500 DB connections, and you have to run some numbers, and the check comes out to be, well, then that means you can only support this much in your execution thread pool, or else a lot of your jobs would start failing. And we don't reserve 1 DB connection per thread. The DB connections are returned back to the DB connection pool as soon as possible to maximize its use. So then, and we work out some numbers to make sure that if you have this much with this many number of worker threads, normally, unless you see some exceptions, the system will not run out of DB connections. And so then the requests may take a long time because let's say you configure 10 DB connections. Well, then you got maybe about 5 worker threads. Then 100 requests come in, and that requires resources. Those requests are going to take a long time because you don't have enough worker threads and DB connections to make it work. But you can also increase it. You can scale your DB that way. Scale your DB better and change it for a management server, and the management server will work better. So there's actually a much harder problem. This is only for incoming requests, right? So anything that's generated from the user, from the administrator. But those unless you're under some sort of a DOS attack or someone who was scripting against your server and has a bug and sends thousands of requests to you, that's generally not the problem. The problem is CloudStack actually performs a lot of tasks on behalf of the administrator, where it is trying to figure out what at what state the entire system is at. These tasks include VM sync, SG sync, security group syncing, and if security group is enforced, hardware capacity monitoring, virtual resource usage statistics to generate any of the usage data for building, things like that. I'm sure that there's more than this, and there will be more to come. And when you're doing these type of things in number of hundreds or maybe thousands, it's not a big deal. But when this number increases, then the problem magnifies. So then the question is, how do you actually scale this across the management servers? So it's not really two approaches, but let's do a comparison of two of the things that you see in CloudStack, where there are these background tasks that are doing work on behalf of the administrator. There's a stats collector. This was written in our version 1.0 product and still exists in CloudStack today. And this is the thing that I said you have to disable. It collects capacity statistics for the host, for the storage. It fires every 5 minutes to collect stats. It follows a smart server and dumb client, or what I call smart server and dumb client model, where basically the client just collects the information, and the information is always processed by the management server. And it runs exactly the same way on every single management server in the cluster. And then there is also VM sync. VM sync was also written in 1.0. It fires every minute. It follows what I call a peer-to-peer model, where the resource is trusted to do the right thing, and when it returns information. And there's what we call full sync and on connecting to the resource. This means all information about that particular VM, about VMs on that particular host are returned back to the management server and compared to what was on the management server. And then from there on, it does what we call a delta sync. And a delta sync means that only out-of-band changes actually gets transferred back to the management server. VM sync is only run against the resources that are connected to a specific management server node. So there are other management server resources connected to management server node 2 is never doing a VM sync against management server 1. So let's do some numbers. So in approach, so we assume about 10K hosts, about 500K VMs. That's fairly reasonable nowadays with 50 VMs per host. On the stats collector, it fires off 10K requests every 5 minutes. It's about 33 requests a second. And it's not too bad. A big server probably can still handle that. Occupies 33 threads every second because each thread is waiting on agent connections or commands that are being executed on the resource. But there's more. Because it does the exact same thing for each management server, as you scale the management servers, it gets worse. On 2 management servers, it goes 66 requests. 3, it goes 99. Then it scales the number of requests it generates actually scales with the number of management servers.
Quick question on that is, so are you guys actually distributing the request so it will be X per second, or are you going to get hit with however many thousand requests?
This is actually already distributed because if you look at it's 10K requests for 5 minutes. So it's 10K divided by 300 seconds. So this is 33 requests per second already.
But so that's what I'm saying, is it only going to do so many every second, or is that stats collector when it fires off after 5 minutes going to go 10,000 go fetch?
Yeah, so it goes off. Well, it's distributed because it's a single thread firing off these requests, right? So it does get distributed over the 5 minutes. But that's not really the big problem here. The big problem is the sheer number of requests it generates is already overwhelming, and so then it gets worse because that's just the number of requests. As when in the management server, there are certain resources connected to one management server and another set connected to a second management server. And because it generates the same requests on both sets, then these requests also gets cross-routed. And there are threads handling that cross-routing. And so the number of threads it occupies is actually much higher. And so our notice is that when these things happen, or when this guy is running, and the management server is at 20% busy, even with no load from incoming requests at all. So that's one thing. And whereas on VMsync, what we do is we fire off one request at resource connection time. It syncs about 50 VMs, takes a few seconds, 5 to 10 seconds, and then it pushes from the resource because we trust the resource to know the things that it has in the last sync point, and it only sends out changes that were not expected on the management server. And the management server respects the fact that the resource will do something correct. So essentially, we have no thread occupied for a much larger data set because this data set is for 500K VMs, and there's nothing, not much processing at all happen for VMsync. And so, an interesting thing about this. So I kind of wrote VMsync, right? I'm pretty smart. The guy who wrote the stats collector is still with us. He's our director of engineering now. So that's the difference between management and an engineer. I'm just kidding, but Will is a really smart guy. This was obviously a 1.0 product, so but it's still in here for 3.0. So obviously I believe VMsync is great, right? But what's the downside of VMsync? And the resources have to reconcile the VM stakes by the management server and the VM stakes that it has. So it has to do more work than the management server. And so then, therefore, the resources require more CPU. And then the resources also need to use a lot more memory because there's a lot of information to keep track of for each VM. But the great thing is that in the data center, these two resources are abundant. There's plenty. If one VM is not enough, you create another VM. Start off 10, 20, 30 resources, and it will be plenty. So we're making use of things that are actually abundant inside the data center versus things that are not. And so then, and it goes on to the, I also want to dive into this other problem a little bit of this stats collector. Not only is the algorithm a problem, but it's also a problem because it did not divide its work depending on the number of management servers. So it gets worse because everyone is handling every single object inside the that's managed by our management server. So in CloudStack, we have a load balancing of all management and resources. As you add another management server into the cluster, the management server will pick some VMs. Will pick some resources, and it will signal to another management server and says, "You need to hand this over to me because I'm here to offload some of your work." Our management server 1 will wait for the commands on the resource to finish, and then it will hold all further commands in the queue. Then MS1 will tell MS2, you can now take over. MS2 connects to it, signals back to MS1 to complete the transfer, and MS1 will discard the resource it was holding and flows the commands or routes the commands over to MS2 to be executed, to be sent down to the resource. And so then we can do a very seamless rebalancing of resources handled in the cloud, in the management cluster. The listeners, and then what we do is we allow you to register listeners to see what what resource is connected to which management server or has disconnected. And then you can actually process those. You can do your processes according to what resources is on your management server. So then by doing that, then you are automatically balanced as management servers go in and out of the cluster. And it also reduces the amount of message routing in between the management servers. So it kills two birds with one stone. Any questions? So designing for scalability. So these are kind of the lessons that we learned. So one thing unique about cloud is that there's abundant CPU and RAM. And in our design, in the management server design, we take full advantage of those two resources. Auto scale to the least abundant resource, and inside a cloud management layer, that's actually the number of DB connections that you have. So you need to auto scale to it, because if you lost the number of DB connections, and things will start failing and left and right. And so you need to be able to auto scale to that. And I think I mentioned this before, do not hold DB connections across resource calls, because the resource calls usually take a long amount of time. And usually, if let's say you start a transaction and then you start a 10-minute resource call, by the time you come back, that transaction would have rolled back because it would have timed out. And no matter what amount of timeout you put in, and you can always find a case where it took longer than that timeout on the resources. So we advocate using lock table implementations if you really do require locks across resources. There is an implementation for that called Merovingian 2, which is also created by our generic DAO, which is used by our method called acquire lock in table in generic DAO. We're perfectly fine with database roll locks, but it's got to be very quick. And we will check when you send messages over to the resource that you are not in a database transaction. And we will assert if we see that. And then balance your resources, the tasks that you have on the management servers. And as it increases and decreases, get notified so that you can so then you can adjust to that, and using job queues so that you can first store the number of jobs that you have and then process them as your resources become available. Okay, that's basically what I have for scalability. Any questions?
You say database isn't the issue, but what about spreading out reads and writes over different databases? Will it make any difference? If it's possible.
But we're only talking to one database.
Yes, but is it very expensive for the management service to connect to the database? For example, API calls which only involve reading. Would it make any difference?
Ah, I see. Yeah. Oh, it absolutely will make a difference. And so then there is a different level of scalability in terms of how to scale the database. That's, we can get a DB admin or someone to go work on that, because that would be somewhat transparent to CloudStack. Because inside our DAO layers, inside our transaction layers, we can always say, if it's reoperation, go to this particular endpoint, and if it's write operation, go to the master, for example. So it's possible, but that's why it's not included in this.
Okay.
In this. Yeah.
So you could read from the slaves, right?
Yeah, that's exactly what Guido is talking about. Okay, so I'm going to move on to the next question. So we learned a lot about reliability with CloudStack, and anybody who runs a data center would kind of know this already. So I might be preaching to the choir here, but I'm going to preach anyways. So it's the 5 W's of unreliability. What is unreliable? And it would be everything. Everything will fail. Everything will break down. Who is unreliable? It will always be the developers, administrators. And turns out the end users are actually more reliable, because they are very reliable to call you, when there's something wrong. You restrict a lot of them, and there will be no problem with what they're doing. And then something goes wrong, they will definitely give you a call. And when does unreliability happen? It's always 3:04 a.m. You know, or I'll take the answer anytime. And where does it happen? And in very carefully planned, everything has been considered data centers. No matter what you do, it still will happen. And how does it happen? You know, kind of just happens. And because you can't plan for everything that can happen. And one thing I want to talk about is that in the who is unreliable case is for the developers. I mean, people make mistakes as administrators and things like that. But for developers, you will have bugs, and that's what causes unreliability, right? So how do you deal with this? So the one thing that you should do is don't assume anything. And so and I have a kind of a story about this, and it really kind of relates to me very well. I purchased a Toyota Prius, about 2009 Toyota Prius. It's a good little car, runs pretty well, saves a lot of gas. And in Thanksgiving last year, then I drove it down to LA. And on the way back, I was in stop-and-go traffic. And there was a long stretch of time where people would just stop. So I turned off the car. And when the traffic starts to go again, and it wouldn't start up. And I looked and I looked, and I could not figure out why it wouldn't start up. Then I thought, it doesn't start up. Let me at least push it off the road and let the traffic beside me go, right? I can't push it off the road. You cannot shift it into neutral when the battery is dead. Yeah, because the whole thing is controlled by software. And whoever made that software assume you will always have electricity. And it is just the worst thing ever. I just could not believe it. There were people yelling at me, yelling at my kids. My kids were climbing around in the back of my car. I still have a message on my phone with Toyota support where I'm trying to get them to pay me for my bad experience. I just could not believe these guys. I thought of that. But I do the same thing when I write software, because I assume something is not going to fail. And at one point, my VP of engineering, when I told him this story, he says, "Oh, karma sucks, right?" Because I did the exact same thing when I was writing, and a lot of engineers would do a lot of the same things. And so it's very important that you don't assume that things just do not fail, and don't bang your head against the wall. And I don't mean that literally. Don't bang your head against the wall means that when you're writing the code, if something fails, you should think about why it failed and whether or not you should retry. And there will be code that retries all the time. Who was on the dev list here? Yeah? Who sent out the email that says, "Why are you spamming me with the build fails?" That happened just before this conference. Did you all get it? You know, that's bang your head against the wall. You know, it failed already, man. Stop trying it. You know, at least know that it happened. So, and CloudStack actually requires a lot of work in that. We're really in the infancy of learning these lessons, and it's because we are trying to get it to a point where we can an administrator can stop the operations in CloudStack and so that it doesn't. They don't need to keep looking at the same exceptions throughout CloudStack. And I like to relate that to you because this is a lesson that we learn. You know when you don't know any better. So I think one thing that developers think is software is magical. And I like to believe that. And it really is, because it creates a lot of magical things. But the fact is that there comes a time when you're in the data center, and the only person who knows what went wrong is that administrator going to the source of what went wrong and looking at it. You sitting there assuming that it will come back, it will get better, would be the wrong choice. So you have to stop and alert someone and ask them to help you. Ask the administrators to help you. In CloudStack, we put in a lot of different things for that. So for example, in CloudStack, we can, when you stop a VM, or a VM is in a poor state, because let's say we send the start command over to a certain resource, and the resource never came back, and it takes a long time for it to come back, and it's stuck at that time. And then when you say, oh, I want to stop the VM, CloudStack goes to look at it. But CloudStack can't reach the resource again. And so I cannot tell you the VM has stopped because I cannot reach the resource to confirm that it's stopped. But an administrator can do that. An administrator can go look, can go there, or he can go through a DHCP and just drop the power connection on that host because it is in bad order, right? But to CloudStack, even though if you did that, I couldn't reach the host. What can I do? We've added flags for these stop commands that says, just go ahead and release because I know better than you, know better than your software on what to do. When you're writing software, that's the things that you actually have to consider in terms of unreliability. But there are things that CloudStack does in terms of making sure that unreliability does not affect the data integrity inside CloudStack. Is Kelvin here? No. Okay, so Kelvin is another architect on CloudStack, and he wrote majority of these things. And where the management servers in the cluster will keep a heartbeat with the DB, and it will self-fence if it cannot write the heartbeat. While other management servers will alert to its components that a certain management server is now no longer writing to the heartbeat and probably have self-fenced. And the code that we do on start VM, on a number of our VM operations, and actually checkpoints, so that if one management server has been deemed to gone down, then another management server will come back and says, as you're at this checkpoint, roll it back. And there might be places where you cannot, like, for example, where we have already sent the start to the resource, and we don't know for sure if the resource has started the VM or not. And in those cases, then we need the administrator's help. And we provide the APIs for the administrators to help us. And we guard against our own mistakes by not actually deleting the rows from the database, so that someone can actually go through and says, oh, I can actually recover certain things from the database, or see at least what happened in terms of the data. And someone would need to go through and write some scripts to clean up the database every so often, but it's not too difficult to do that. Write code that is idempotent. Write code that says, I'm going to check these things each time, and repeat those things each time, so that if I was at a certain stage before, I know how to go from that stage again. And write code that reuses code that's been proven versus a different unbranched code. One example that I have is that on a management server going down, our resource connections are exactly the same as when the management server starts up. It goes through the exact same code. We don't have a separate line of code that says, oh, if this management server go down, this is what you do. What we do is mark all the resources as disconnected, and then we have separate threads that brings them up and let it compete against other management servers to load, so that it automatically spreads across the remaining management servers. Things like that where we use the same code for different situations. And same thing with HA that I was talking about yesterday. We use the same startup code. We just do a few more extra steps before that to ensure the startup code is back at the condition that it expects it to be. And respect modularity when you write your code, because one of the worst things is that you go across boundaries to fix something that you think you know what you're doing, and then actually turns out it doesn't. Any questions? or comments? Okay, so I guess we're going to get to the free-form portion of our discussion. So who are the developers here? Oh, no, I meant the CloudStack developers, because they need to come up here and help.
We can cover anything on the bare metal.
Frank. Questions about bare metal? Yeah, I actually didn't have one prepared because I wasn't sure if there's anybody here who's working on hypervisors. But Frank is the one who implemented the bare metals, so he'll be able to answer. Hey, you can just use this.
So I don't have any slides, so if you have any questions, you can just ask. So about.
Maybe you can talk about how you did it.
Oh, okay. So, I'm sorry. I'm sorry, I don't have any preparation. So currently we are working on the bare metal 2 in CloudStack. So at the very beginning, 1 year back, we started working on the bare metal 1. It basically it uses PXE server to store the disk image, and then you can just like okay. Let me arrange my mind. So how to describe? Okay, so in CloudStack, basically, you manage the virtualization VM, and the bare metal, I let you have a capability to manage the real host as the VM in CloudStack. So you can control the real host, the bare metal host, like just a VM in CloudStack UI. So what? So the technology is behind it is the PXE and the IPMI. So basically, you can add a bare metal host as a user host, like the Zen server in CloudStack host page. And basically, you need to fill up the MAC address, the IPMI address. IPMI is a protocol to control the bare metal host. So once you've done it, you have to register an image. The image in CloudStack bare metal 1 is the ping image. The ping is an open source software. You can use this software to take a whole disk image from the bare metal host. And then once you have it, you can register it in CloudStack UI, just like a template of the virtualization template. And then you can go to the instance page and select the service offering to specify you want to spring up a bare metal VM and specify the template name. And then CloudStack will pick up a host from the bare metal host cluster, and then provisioning that image on that host. So basically, we use IPMI to set the host to next start as a PXE start, and then we program the DHCP server to assign the IP address to that host and give the link to where to get the template. And then we use IPMI to reboot the host. Once the host springs up, it uses PXE to download the image. Basically, we will run a small Linux kernel in RAM and prepare a RAM disk and mount the NFS share, and then use the ping software to clone the image to your disk. So once it is done, so in CloudStack UI, the bare metal host just like a VM, like a virtualization VM. So you can manage both virtualization VM and the bare metal machine in the same UI and with the same consequence. So that's okay.
Okay, and a question: the DHCP server, how is it provisioned and where is it running? Because there's no.
Oh yeah.
You need a host where DHCP is running on.
Yeah. So basically, in CloudStack, we call the part is a broadcast domain. So basically, before you provision the bare metal host, you need to start a VM or what machines in that part, or install CentOS or whatever. So then you register this host with IP address as a password and account in CloudStack. So we control the we control the DHCP daemon or the DMS MySQL daemon on that server as our DHCP server. So. Okay.
So do you need hardware IPMI on the motherboard in order to use your CloudStack on bare metal?
So you mean the IPMI protocol version or?
You need the hardware on the motherboard?
Yeah. So basically, yeah, we need the IPMI support in BIOS of the host. But currently, almost all the server hosts have that capability. Yeah.
I had a question. So you were talking about the images.
Okay.
So is there any mechanism to transfer the VM image back into, so the templates into the physical one, or is there anything?
Yeah, that is possible. So basically, right now there's multiple the peaked how to call it. So the P2V or V2P, the image convert. So basically, if we write a tool ourselves, we can convert the then server VHD image to the host disk format. We can directly provision the VHD image on the host. But currently, CloudStack only supports that.
Question, does a bare metal host need an agent software install, or is it?
Right now, we don't need, because basically what we are doing is just clone the template onto a host. We never touch the inside of the operation system. But in bare metal 2, we are supporting the Kickstart file. So right now, we just clone like a ghost, clone the image to the disk. In bare metal 2, we will use the Kickstart file to install the Linux operation system. And then we will support the security group. Security group, you guys may know it's a firewall in CloudStack. Then we will install an agent in the operation system. Then we can just use the same same tool in security group to program the bare metal host. Yeah.
So,
Sorry.
Go ahead.
Go ahead.
Sorry. For which action do you need IPMI? Only to boot it with
Yeah.
DXA, or?
So basically, we need the boot, reboot, and stop the host. We need the IPMI tool.
But you can also do that with power commands, but it's not supported.
Which command?
Now, I mean, a lot of old servers don't have IPMI.
Oh, yeah, because when we design the bare metal in CloudStack, we just choose what's the popular technology current server using. So IPMI is the first thing coming in my mind. But for latency, the server currently we can't support that.
But it should be possible to build it also with the power commands for servers like start, stop. So I'm still not sure what if you don't have IPMI on the server.
If you don't have IPMI, I don't know how to control the remote host.
Like the APC.
Yeah,
that's the power strip, yes.
Okay, so if that's possible, we can also support in CloudStack, because we are just integration. If there is some tool in Linux, we can send the command to the host. We can just use that integrate with the CloudStack to support.
Okay.
Yeah. So why Kickstart for bare metal 2.0? Kickstart. While I'm perfectly happy with Kickstart, there are a lot of operating systems that barely support Kickstart or don't support it at all. So can you tell me a little bit about why the choice for that, and not something breaking that piece out and using something that isn't CloudStack to handle provisioning for those bare metal hosts?
So the question is why we choose the Kickstart file as the technology for bare metal 2. I'm right? Yeah. So So sometimes you need to make the decision, because right, most customers are using the Red Hat based the Linux operation system, and the Kickstart file is the default for the Red Hat. So we just want to the first step, we just support the most popular technology in the world, and then we can just step by step to extend the technology to cover more operating systems. Yeah, there's no technical the issues here, I think.
I just wonder, if you do Kickstart, then the next, if you wanted to do some other type of operating system, then you'd have to continue to layer those on.
So you can, for the operation system only support the Kickstart, you can go back to the bare metal, the 1.0, so just clone the disk image and register as a template. Because for the template, there is no limitation for the what sort of the operating system, right?
But for Windows,
Yeah.
the ghosting works better, right?
Yeah, for Windows, I'm not sure if ghosting is better, but because we are using the small Linux kernel, so the part image may be the default tool for that purpose. I'm not sure if Ghost supported Linux. I really don't know.
So I see a lot of provisioning tools that are starting to have an API. The one that immediately jumps to my mind is Cobbler, that you could have sitting there as a service that you integrate with or require them to use. And then CloudStack just talks to the Cobbler API, which takes care, and Cobbler, because it's a provisioning tool rather than an infrastructure as a service tool, knows how to deploy everything from switch stuff to whatever.
Yeah, actually, I'm still looking for the open source, some kind of the PKC infrastructure to do such things. Actually, at the bare metal 1.0, at the very beginning, we try to integrate with what called is a Lean. Lean is a commercial whatever PKC framework. But at last, it won't work because sometimes you integrating with some software, you don't know what the underlying implementation. And at the very last, when customer did it, and it have some trouble, and you cannot figure out. That's a really bad experience. So for bare metal 1.0, we choose Ping as it's open source. And as you're suggesting, I think Clara may be a candidate. I will look. Yeah, actually, I already looked at it before, but it's a couple of months ago. Yeah, and really there's many candidates. We just want to choose the most proper one for the bare metal 2 there.
Well, yeah, I'm happy to start the discussion about bare metal provisioning tools on the mailing list, and maybe we
we can
can
start
get people's
discussion on the
opinions
mailing
other
list.
than ours involved in that.
Certainly something I'm very interested in as well. The whole stateless provisioning of hypervisors and running them gives you a lot of flexibility. I think we heard Peter from Disney commenting that that's how they're running their system. It's kind of a natural extension, and it seems like the perfect operating model for running CloudStack-based cloud.
What could be even a addition to it? If you have IPMI control over all hypervisors, in the night when demand is low, you could also shut them down.
Yeah.
To save power. If you're
You could even do that without IPMI.
well, yeah, but getting up again.
Well,
Yeah.
I want to be careful though. I don't want to see anything tied too tightly into IPMI. Use it if it's there, if it provides a benefit, but there's an awful lot of cloud hardware out there these days that don't have IPMI control.
Oh no, IPMI
and
suggests
IPMI means a lot of different things too, right? So just because you have IPMI stamped on the literature doesn't mean that implementation is going to be the same across all hardware. That's fairly standard, especially with later IPMI implementations. But if you get much past start, stop, or start, reboot, you're wandering into dangerous territory. And that comes back, do we really want CloudStack to become a hardware management? Maybe we do, maybe we don't. Maybe we want to interface with something that has a nice API that does that already.
Yeah, sometimes it's just a choice.
Yeah, but it could be a pluggable service or something where you can say, okay, use IPMI for shutting this host down, or use a power PDU for this, or whatever is available.
Correct.
But the point is, you could scale out your machines whenever demand is low, shut them down, and bring them up again. It could save a lot of power and a lot of money.
Yeah,
Correct. Yeah. Okay. So actually, I was thinking if we can just use bare metal to provision the hypervisor, that will be easier to manually install rather than server KVM. So we provide the total solution, both for virtualization and manage the hardware. That would be easier to customer. Okay.
But don't you have then the problem with different disk size?
Disk size, yeah. So
if you use it,
yeah. So for bare metal, the P image can handle that. So basically, if the image only 8 GB size, and you have 100 GB size disk, it will fill there to the empty disk and to expand the whole disk. That was solved by the image format.